Humanoid robots can potentially replace humans in hazardous environments. If these robots can imitate humans with precision, they can also be utilized in a variety of other fields where they can collaborate with humans.
The objective of this initiative was to create a novel torso mechanism that could be utilized in a humanoid robot. The newly created mechanism can move in flexion extension, lateral bending, and rotational bending, much like a human torso. It also includes a unique imitation spine that lessens the force in the torso actuators while contributing to the robot's anthropomorphism.
The design of the torso is heavily derived from the human skeletal structure. There is a main vertebral column structure that consists of rigid vertebrae with flexible intervertebral discs. Attached to the vertebrae are the ribs, which connect to the sternum at the front of the torso. The main actuators of the torso are attached from the base to a middle plate that bridges the sternum to the spinal column. This design allows for the movement of the torso to be tuned with many different factors to achieve the movement and appearance goals more easily.
All parts of the torso were modeled in SolidWorks and 3D printed. The entire torso and each individual part went through multiple iterations before the final version was established. The custom linear actuators went through 3 distinct iterations with many small refinements as time passed. Linear actuators that are compact, have velocity and position feedback, and meet the torque requirements are both expensive and not easily accessible. To keep the project within budget, custom linear actuators were developed and manufactured. The actuators fit within the torso and use inexpensive geared motors that allow the actuator's speed and torque to be changed with different motors while keeping the size of the actuator consistent.
The torso functions in a two-part system. A MATLAB script running on a host computer calculates the length the actuators need to be at to achieve the desired position. The movement command is then sent to an onboard Arduino Mega via USB cable, and the actuators move accordingly. The MATLAB script has a graphical user interface to allow the user to more easily control and view the torso positions. The GUI has sliders that allow the user to quickly and accurately control the torso's roll, pitch, and yaw angles. To the left of the control section, a simulated view of the torso is displayed at the desired angle.
The torso mechanism has the following mobility: a flexion extension range of 20 and 28 degrees respectively, a lateral bending range of 14 degrees in either direction, and a rotational bending range of 40 degrees in either direction.
A novel torso mechanism was designed that could be utilized in a humanoid robot. In addition to the design, the torso is manufactured, programmed, and tested to ensure its compliance with the original objectives, to have degrees of freedom similar to a human and to look humanoid on the surface.
This torso design allows for many different avenues for improvement and expansion. In addition to finding the task space computationally, the spinal column can be optimized for different loading scenarios, and the cervical spine and head can be added to the robot. The novel spinal column design in particular presents new opportunities for humanoid robot design in the future.